Chapter 12 of Astronomy, the Science of the Heavenly Bodies. Astronomy, the Science of the Heavenly Bodies by David Todd. After the Great Masters. Following Kepler and Galileo was a half-century of great astronomical progress along many lines laid out by the work of the Great Masters. The telescope seemed only a toy, but its improvement in size and quality showed almost inconceivable possibilities of celestial discoveries. Hevelius of Danzig took up the study of the moon, and his selenographia was finally illustrated by plates which he not only drew but engraved himself. Lunar names of mountains, plains, and craters we owe very largely to him. Also, he published, among other works, 2 on comets, the second of which was published in 1668 and called the Cometographia, the first detailed account of all the comets observed and recorded to date. Many were the telescopes turned on the planet Saturn, and every variety of guess was made as to the actual shape and physical nature of the weird appendages discovered by Galileo. The true solution was finally reached by Huygens, whose mechanical genius had enabled him to grind and polish larger and better lenses than his contemporaries. In 1659, he published the Systema Saturnium, interpreting the ring and the cause of its various configurations, and the first discovery of a Saturnian satellite is due to him. Gascoigne in England, about 1640, was the first to make the important application of the micrometer to enhance the accuracy of measurement of small angles in the telescopic field. An invention made and applied independently many years later by Huygens in Holland and Azou and Picard in France, where the instrument was first regularly employed as an accessory in the work of an observatory. Another Englishman, Jeremiah Horrocks, was the first observer of a transit of Venus over the disk of the Sun in 1639. Horrocks was possessed of great ability in calculational astronomy also. This was about the time of the invention of the pendulum clock by Huygens, which, in conjunction with the later invention of the transit instrument by Romer, wrought a revolution in the exacting art of practical astronomy. This was because it enabled the time to be carried along continuously, and the revolution of the Earth could be utilized in making precise measures of the position of sun, moon, and stars. Louis XIV had just founded the new observatory at Paris in 1668, and Picard was the first to establish regular time observations there. Huygens followed up the motion of the pendulum in theory as well as practice in his Horologium Oscillatorium, 1673, showing the way to measure the force of gravity, and his study of circular motion showed the fundamental necessity of some force directed toward the center in planetary motions. The doctrine of the sphericity of the Earth being no longer in doubt, the great advance in accuracy of astronomical observation indicated to Willebrord Snell in Holland the best way to measure an arc of meridian by triangulation. Picard repeated the measurements near Paris with even greater accuracy, and his results were of the utmost significance to Newton in establishing his law of gravitation. Domenico Cassini, an industrious observer, voluminous writer, and a strong personality, devised telescopes of great size, discovered 4 Saturnian satellites and the main division in the ring of Saturn, determined the rotation periods of Mars and Jupiter, and prepared tables of the eclipses of Jupiter's satellites. At his suggestion, Richer undertook an expedition to Cayenne in latitude 5 degrees north, where it was found that the intensity of gravity was less than at Paris, and his clock therefore lost time, thus indicating that the Earth was not a perfect sphere as had been thought, but a spheroid instead. The planet Mars passed a near opposition, and Richer's observations of it from Cayenne, when combined with those of Cassini and others in France, gave a new value of the Sun's parallax and distance, really the first actual measurement worth the name in the history of astronomy. To close this era of signal advance in astronomy, we may cite a discovery by Romer of the first order, no less than that of the velocity of transmission of light through space. At the instigation of Picard, Romer, in studying the motions of Jupiter's satellites, found that the intervals between eclipses grew less and less as Jupiter and the Earth approached each other, and greater than the average as the two planets separated farther and farther. Romer correctly attributed this difference to the progressive motion of light, and a rough value of its velocity was calculated, though not accepted by astronomers generally for more than a century. Why the laws of Kepler should be true, Kepler himself was unable to say, nor could anyone else in that day answer these questions. 1. The planets move in orbits that are elliptical, not circular. Why should they move in an imperfect curve rather than the perfect one in which it had always been taught that they moved? 2. Why should our planet vary its velocity at all, and travel now fast, now slow? Especially, why should the speed so vary that the line of varying length joining the planet to the Sun always passes over areas proportional to the time of describing them? And 3. Why should there be any definite relation of the distances of planets from the Sun to their times of revolution about him? Why should it be exactly as the cube of one to the square of the other? We must remember that the Copernican system itself was not yet, in the beginning of the 17th century, accepted universally, and the great minds of that period were most concerned in overturning the erroneous theory of Ptolemy. The next step in logical order was to find a basic explanation of the planetary motions, and Descartes and his theory of vortices are worthy of mention, among many unsuccessful attempts in this direction. Descartes was a brilliant French philosopher and mathematician, but his hypothesis of a multitude of whirlpools in the ether, while ingenious in theory, was too vague and indefinite to account for the planetary motions with any approach to the precision with which the laws of Kepler represented them. Another great astronomer whose labors helped immensely in preparing the way for the signal discoveries that were soon to come was Huygens, a man of versatility as natural philosopher, mechanician, and astronomical observer. Huygens was born 13 years before the death of Galileo, and to the discovery of the laws of motion by the latter Huygens added researches on the laws of action of centrifugal forces. Neither of them, however, appeared to see the immediate bearing on the great general problem of celestial motions in its true light, and it was reserved for another generation and an astronomer of another country to make the one fundamental discovery that should explain the whole by a single simple law. End of chapter 12.